Okay, we're looking at 5.5, the collision model. So molecules must collide to react, but only if a small percentage actually create reactions. So there must be other factors than just colliding. So they first must have sufficient energy to produce a reaction. Remember, we need to break bonds in order for new bonds to form. So equal or exceed what's called the activation energy. They also must be correctly oriented with one another to produce a reaction. So the idea is that if it's trying to react the one end of a molecule, but it's coming in backwards, it can't line up in order to overlap the orbitals that it's meant to react with. So the bigger the compounds are, the harder this usually is because you have kind of more areas where this could go wrong as opposed to where it could go right. Now, this idea is that the number of species that must collide to produce a reaction is indicated by that step. So if it's unimolecular, such as something like a molecule breaking apart, that would be one molecule. Bimolecular, collision of two species. Termolecular, three species. So this gives us the idea that if it was by itself, it's rate law, pretty much straightforward. You have the idea of bimolecular, to where if you have two of these come together, so two of the same, it'd be A squared. Obviously, two separate, you'd have them each individual. Termolecular, like two of these sandwiching around a B, or all three being different, kind of their ideas of rate law. So when we think of effective collisions, there's kinetic energy. The energetic collision leads to a product. If it's not energetic enough, you get no reaction. The reacting molecules must have sufficient kinetic energy, which is related to temperature, so that they can collide with the activated complex can form. The activated complex, thinking of if you have your reactants and your activated complex is like everything smushed together, all the bonds broken, not formed yet, so it's at the top peak of our activation energy. There's also orientation factor. So if the idea is that these need to overlap, in order for us, I should say the chlorines need to overlap in order for it to make a chlorine molecule, ineffective collision would have like the oxygens come together, or an oxygen and a chlorine. We need to have them line up in order for this to occur. Now, of course, due to the kinetic molecular theory, these are all random. Okay, so based upon this occurring, the more collisions we have, the more likely we're going to have what's called effective collision, meaning that they're going to line up with enough energy. So there's some ideas of interpreting the factors affecting the rate. Again, we come back to the reactant nature. Things will often occur much faster in solution than in pure substances. So we have like two ionic compounds, for example, solids. If you mix them together and they are meant to react together, such as having let's say two soluble compounds like sodium chloride and silver nitrate, in their powder form will react to make silver chloride a new precipitate. However, that'll take a very long time for those ions to come together and have an attractive force to overcome what's already there. In solution, both compounds would be dissolved, therefore separate, and all they need to do is overcome the ability of the water molecules to attract, and that actually happens very easily. In solution, it gives much more particle contact. They're separated, which means allow more effective collisions rather than the solid chunks forming on each other and not being able to move. And of course, forming solutions breaks those bonds that need to be broken. So you've already kind of got a lot of aspects there happening in solution, which is why our body has so much water in it. As a solution, or primarily a solution, a lot of chemical reactions can happen at a lower energy and happen much simpler than if they were in the solid form. Now, some things go faster or slower because they have maybe a higher initial potential energy, therefore closer in energy to the activated complex, or because their reaction has a lower activation energy. These may seem similar, but the idea is that if we have a higher potential energy, let's say the peak was here, if we have a higher potential energy, now we need less energy to get to that peak. Otherwise, we could also have another one that has a lower potential energy. The difference is the same, but it's two different reasons. So for example, if we have methane react with chlorine, this produces the products about 12 times faster than if we have what's called, you might be going, D, what's D? D is what's called deuterium. It is a isotope of hydrogen. Hydrogen only has one proton, no neutrons. Deuterium has one proton and one neutron. So it's a little heavier. So because the CH bond is a little weaker and less stable than the CD bond, this happens 12 times faster. So it's a little bit higher potential energy. Otherwise, though, something like with this reaction of methane with a halogen, with fluorine it occurs 100 times faster than chlorine because the activation energy is much less. So if the activation energy is much less, it's going to happen at a faster rate. Other areas, the molecular interpretation with concentration, generally increases as the concentration or pressure increases, except for zero order reactions, because zero order we've already determined does not change based upon concentration. More molecules leads to more molecules with sufficient kinetic energy for an effective collision. Distribution is the same, but it's just a bigger curve, meaning a higher curve. Now, when we think about temperature, temperature raises average kinetic energy, which actually has two roles. That means that the minimum amount needed for a collision to be converted into enough potential to form the activated complex. So more kinetic energy means we can have higher activation energy. Increasing the temperature increases the number of molecules. Therefore, we're going to have more overcome that activation energy. So temperature also includes the number of collisions, right? Because things are moving faster, you're going to have more collisions at a higher energy. So this is why temperature has a pretty big role. If you think back to when we talk about 10 degrees Celsius increase, usually around doubles the reaction rate. So the couple of things we've already been talking about, we have things like the potential energy of the reactants and products, the activation energy, and kind of taking our raw ingredients, our reactants, and getting to what's called the activated complex at the peak, where everything would be broken apart, ready to form those new compounds, and therefore be at a lower energy. So the idea is that thermal energy is distributed. Even though we might have a temperature that we can say something is at, there's a distribution of temperatures, as learned with the Maxwell distribution. So as temperature increases, the fraction of molecules with enough energy increases. So you can see the area under the curve. When temperature 2 is higher, the fraction of molecules is more spread out, but we can see that there's a higher number of them that are going to be past the activation energy than if it was at a lower number, a lower temperature. And that's where we end off with this idea of 5.5. Come in with any kind of questions and I'll be happy to answer. Take care.